Hello, everyone. Hopefully, conference has been fun so far, and we're going to be talking about like containers and layers, and we're going to talk about NICs. And the idea behind this is to kind of inspire some thought and to give everyone a little bit of a sense of like, hey, like what are some things we can do? What are some possibilities? We don't really have all the answers, but just to kind of start conversations. That's kind of the whole point of this thing. We do have some ideas about where this can go and like why we're interested and passionate about this kind of overall topic, but maybe there's new things to be excited about that we don't even know about yet. So if something kind of strikes your fancy, please let us know, and well, we can do something and make something out of it. So I'm Tom Bereknyei. This is Leigh Capili, and let's get started. So that was us. We're going to talk about the OCI layer paradigm and maybe how to disrupt it. We're going to do this now. We just did a bunch of these sorts of talks over at Planet NICs. That was happening yesterday.
Check. Cool.
And now we're at scale. I think, yeah. So let's get started. So containers. Containers are great. They're built from layers. But how many layers can you actually stack together? How do you orchestrate them? Uh-oh.
I was just trying to move that because maybe it was like an analog source that was causing the the feedback. If I stand over here, I'm not getting feedback. If I stand next to Tom, we get feedback. Maybe it's because our mics are pointing at each other.
Turn off or something.
What if I stand here?
That might work.
That's
okay.
Probably, okay. So that's pretty impressive. Because yeah, it's like.
Excellent.
Yeah, there it is. Okay, that's what does it. So Tom and I are, I guess we're like magnetically opposed.
Yeah.
Okay.
Okay. So yeah. So there's issues with when you have containers. Sometimes with with how many layers you've got. Sometimes there's issues with size. Sometimes there's issues with orchestrating these things. Sometimes there's issues with startup. And there's issues of reproducibility. How do I compose them? And some of these things we can kind of fix or address, or like these are just pain points that we have. So we want to kind of start or maybe rethink some of these things and question some of our basic assumptions. That's kind of like the major kind of thought process here. All right, so overall ground rule for this, interrupt me. I do like having questions. I do like to, if something's unclear or if something could be more clear because you might have some insights or some knowledge that is better, then please interrupt no matter what. Otherwise, I will just keep talking and you will have to kick me off stage. So, okay, so we're going to talk about some of the limitations. We're going to talk a little bit about kind of how NICs works and how we think about things. We're going to talk about how OCI images are kind of normally put together, some of the practices that you might see. And then we'll go do a little bit of demo, a little bit of hands-on. We'll do some kind of QA afterwards and some discussion. So our intent here is to be a little bit informal as we go through. So containers. This is like fascinating stuff. It's like at the underpinnings of a lot of the advances we've made in terms of our ability to scale and like run and operate software. And it's like this is great stuff. We bundle applications, we bundle services. We're able to scale them out, move them around. We're able to test them, integrate them, isolate them. And there's a huge ecosystem built around this, right? We've got products and conferences and monitoring and security tooling and terminology, careers built upon this technology. So it's kind of fundamental to a bunch of like the work that we do. But do we fully leverage them, right? Are things we can kind of question? And I always like to kind of come up with ways, can we like change something? Can we question some of those basic assumptions? So one of them that we kind of looked at a few times is that how do we build containers? We often build them in a very layered fashion. And do we have to? I don't know. So generally, when we kind of build containers, we do this, hey, we got a Docker file. We started writing up, hey, here's how I build my application. Here's my base image. I'm going to put my source in there. I'm going to start building stuff. And the way the caching works and the way we distribute these things, kind of makes sense. We think about this as if this was broken down, layer by layer by layer, one thing building upon the next, a series of steps. This is simple, right? Each of these things then gets turned into a layer, and in our mental model, hey, they get turned into something that gets hashed, that gets tarred up, it gets sent up to a Docker registry, it gets pushed around, and then those things get kind of burned in and baked. And this is kind of what works for us. Leigh, you got
I just want to point out, for anyone new, and then also I think we've all become incredibly, a lot of us have become very experienced with building containers. And so Tom said, oh, it's simple, it feels simple. But if you look at actually what's happening in the Docker file on the right, we for each layer, are writing a little script, or we're using a command from the Docker file syntax, from their little DSL. And that script or command is the local cache key for whether or not to rebuild that layer. And then the output of the layer is a content address hash. So that's how we know whether or not it changed, so that once we produce it, we have bits that are hashed, and we decide whether or not we want to send that layer somewhere else. And then the last thing that's really actually kind of special about this data structure is that for each layer, for all of our steps, we actually have a little bit of an order. So typically, we will invalidate this by the order, and we'll run all of the steps afterwards. And the reason that it is ordered is that a layer is actually an overlayFS file system layer. And that's really important, because it's going to do something for us that is kind of limiting. When we build an overlay file system with lots of layers, that has consequences. And I think it's really cool to look at this data structure, because it created a workflow that is so simple, yet so incredibly generic and powerful. And this is why containers are the shape that they are, and why we've built standards around them. But in order for us to move forward, we need to evolve, not away from this, but on top of it. And I'm really excited about that.
So yeah, as we summarized here, this is an amazing way of doing it. It's intuitive. It allows for really good adoption, right? People were able to kind of pick this up. It's a simple mental model, right? And it's effective. And then upon this, we now have a huge corpus of layers. We now kind of manage these things, in the millions. But there are some questions that are remaining, and these are the things that kind of I ask about. Is well, how do we share these things? Okay, we have mechanisms to move them around, but how do I share not the artifact at the end, but how do I share those Docker files, those instructions, those build instructions? How do I share those? Right? Do I just copy them around? How do I reuse them? What about bloat? Right? This very kind of I'm always adding upon the previous layer is going to be very much you can imagine. You're always adding. You're never removing. Right? How do we fix that? There's ways we do this in the industry, but again, it's not kind of built into the mental model that we normally have. How do we establish and enforce and check and make best practices easy to apply? Again, the simple mental model doesn't quite tell us, right? And that's fine. It's good for adoption, but again, how do we make this happen? How do we manage the supply chain? That's becoming more and more of interest for more industries. I mean, some of these situations, we started to build additional things. So then, we added, multi-stage builds. This is a way for us to address some of these issues. Okay, some of them are very easy. Go is an excellent example. Everything gets compiled to one binary, and I can say, go grab a base image with a bunch of stuff in it, add in some dependencies I might need, go bring in my project source code, go get all the dependencies that my project has, right? And then go compile this thing, and then I finally end up with one nice little artifact. And that little artifact, copy that over into my next container, and then now my build is complete, and I end up with something that's nice and clean. That's a really nice model, right? But again, even for this one, you can start to see that mental layer we had before, the mental model we had before is starting to break down. The whole like one layer for each of these in terms of what we're going to expect to see at runtime, again, it's not as clear. Now we're juggling different contexts, we're moving them around. Now this is probably the simplest possible example you could come up with, right? It's a language very nicely tuned to support this sort of a thing, and an ecosystem that supports it. But even this starts to kind of break that model. What happens when you have a lot more dynamic libraries or scripting languages where it's not so easy just to kind of to pluck out that one kind of artifact that you know that you need? What if you get it wrong, right? What happens if it's trying to like DL open something at runtime and then you know, things you expect to have there are gone, and only certain code paths do that? Who knows, right? Language-specific support I want to call out as interesting here because, well, different languages might not be amenable to this sort of thing. Again, then maybe some of them are, but then now you have to kind of have that expert knowledge of both your containerization technology and your language technology. So this is kind of these sorts of things help, but again, you know, what else can we do? So kind of take a quick pause on that. I come from an ecosystem where, you know, I'm fanatic about Nix. So if we want to go talk about Nix, I can do that for another few hours, but I'll try to keep it short and sweet here. Nix is a declarative framework, right? We like to do a whole bunch of like builds, package management, deployments, like in this kind of very you know, disciplined way. Been around since 2003. We got a whole bunch of like open source. We've eventually packaged all of open source, I'd say. And if it's not packaged yet, then it's likely because either it's too hard to package or because not enough people want it. But generally, everything's been out there. We have a big focus on like correctness, keeping track of provenance. So everyone worried about SBOMs, it's like, hey, this technology, this ecosystem has SBOMs just by construction. That's how we build the things. We worry about reproducibility a lot. You know, we call it purity. A lot of the best practices that you might want to impose upon your like ops teams, like, you know, as we do our builds of things, we do this by default. Like, you can't just call out to the internet at random and kind of grab things during your build processes. You know, you're not going to have some sort of like leakage into your system by like home directories and usernames and who knows what, like configurations that kind of leak into builds. We want to make all our dependencies very explicit, right? These are best practices that you kind of want to impose, but you know, here's a system that kind of does it for you or kind of enforces it. Sometimes that enforcement's a little strict, but again, it keeps you out of trouble most often.
I just want to point out a little thing, which is that earlier we mentioned that Docker is such a fantastic virtualization and runtime technology. And one of the reasons that it also became revolutionary is it became incredibly easy with the Dockerfile user interface for people to kind of package something that is runnable and maybe potentially even extendable, right? You could use base images and do some imperative stuff to then get to some other image that you want to run. But you'll notice that a lot of the problems that Nix solves that Tom is talking about here, Docker is completely unconcerned with. And I think what that points to is that Nix is an awesome packaging technology. And Docker images sort of accidentally became a packaging technology. But perhaps we can do better.
Yeah, thank you. So I gave the pros. Here are some cons. Basically, yeah, Nix is famous for a steep learning curve, but this is getting better, right? We're figuring out paradigms and abstractions that make it easier to learn. Documentation's getting better. This is the focus on upstream. I'm working at Phlox, where one of our goals is to kind of bring the power of this technology, but with a much, much simpler user interface to people. So drop by our booth, and that's my plug for the day. We also have a perception problem, right? We're kind of seen as very different and very niche, right? You're like, oh, you guys are like the weird kids over in the corner doing your kind of weird, crazy stuff. You know, came from the academic world and all this theory and all this functional programming. It feels weird to a lot of people. So we need to work on, you know, being able to explain this better and also be able to, you know, communicate better. It's also another interesting situation where there's a lot of like big companies, big enterprise users that kind of rely upon this tech, but it's funny that they don't come to conferences. They don't talk about it. It's interesting. It's sometimes it feels like they consider it like a trade secret. But we're seeing more in them come out about like what this is, be a bit more clear about it. They come to conferences. We started a blog series to talk about like, hey, like this actually is being used in the wild, and to start kind of raise the awareness of that this is a thing. We're running conferences, right? That's kind of why we're here. We ran one yesterday and the day before, and so we're trying to fix some of these issues. Okay, so what's this idea? Layers to graphs. That's like the kind of big picture CS kind of description of like what are we trying to propose here. Docker builds, right? Very linear, one by one by one. We have this ordered list. But normally when we build software, like when I'm building some piece of software, I don't usually think I'm going to take this one program and I'm going to extend it. I mean, that might be how I start, right? Or maybe that's kind of a plug-in style methodology. But usually it's like I'm going to take not just one program and extend it, or one library and wrap it or extend it. Instead, I'm going to take one library that does X, another library does networking, and another library that does like async work, another library that does image processing, and I combine them into some creation that works for me. I need multiple inputs, and I need to combine multiple things. That doesn't quite fit this like linear ordered list model, right? I can't just do like a leaf package, wrapping it, and then another leaf package, another leaf package. Instead, we usually think about like a tree of dependencies, a tree of libraries, things that depend on, right? When you do something like a Go build or an NPM build, this is what you get, right? And this is kind of how like Nix works as well. Nix kind of understands this like tree-like model, a DAG, right? This is a DAG that.
Yeah, all the computer science nerds were like, that's not a tree, that's two trees intersecting with direction. So the directed acyclical graph is what that DAG acronym means. It's a graph with pointers in one direction, and if you've never heard that term, it's no loops. Yeah, there's no loops in a DAG.
Yes.
Yeah, so you're always able to go from kind of the top of the multiple entry points in the DAG to the end of the leaf nodes of the DAG in one direction without repeating or cycling.
Yeah, thank you. Yeah. This also, another thing that you get here, I want to just touch on slightly is when you have these sorts of, like here in this example, I've got a portion of this graph that is kind of a little bit independent until it has to come together. That independence actually means I can distribute this. Let's say these things are very expensive to do, right? And on the right, you can see, hey, like this portion of those green boxes, I can actually distribute that work. So now imagine you could start to describe not just, hey, like a build of some software, maybe that build is very expensive, right? I can now start saying, hey, run some of these jobs on different machines or in different clusters and actually get distribution as a feature out of this, because I'm no longer forced to do things in a serial fashion. So that's something else to consider. Okay. This gets me into a kind of a thing that I care about is, in the end, like packaging. Like, what is packaging? And I think it's something that we sometimes think, oh, it's kind of this annoying thing to like actually get something into production or be able to distribute to other people. That's kind of the point. Packaging makes software reusable, right? Whether this is your end application, whether this is a library. I mean, we could hope that every single person out there is going to build everything from source, but frankly, that's probably not going to work, right? Most people just want their application. They want to just double-click. They want to download and roll. They want their existing package manager to just know how to install your application and upgrade it. So packaging is important. In some sense, I think we've abused and used containers as a packaging-ish format, but it's usually kind of a dead end. Like once you kind of put it into that container, now what? So if you make a library, should you just distribute that as a container? I actually talked to someone that did this, and it was a little confusing. I'm like, well, what if they need to use other libraries as well? Like, now what? They're like, well, they're going to have to use our package manager. I'm like, okay, well, that might work for a little while, but how do you actually end up allowing people to reuse multiple things, right? So I think we still need packaging. Usually, if you go into a container or a Docker file, what do you usually see at the, very near the top? I'm going to apt-get install like 15 things for all my system libraries, or I'm going to like pip install all the requirements I need. Like you're still going to use some other package management system to get it going. So in that sense, yeah, like containers kind of let us kind of cheat a little bit and get away with it, but at some point that cheating, that getting away with it is going to catch up with us. So yeah, so what else can we do? On the Nix kind of perspective of how we think about stuff, we'll say non-Nix world, we use like the file hierarchy standard. You put stuff into like user local bin or libs and all that stuff, and we use a different approach, right? We put everything into a set of store paths, and those store paths have like this cryptographic hash in there, and this way they're isolated. They're not going to be in your normal locations. And what this means is it's kind of like prepending everything with a content addressed hash, right, or a unique hash. And if you do that, now those files, those directories don't conflict with each other. So before, if you only have one thing in user bin, well, that's no longer a limitation because I've prefixed everything with this unique hash. Well, as we're talking about content hashes and things like that, that starts to sound like a container registry, right? If you think a layer, each layer is associated with some sort of a SHA-256 hash. Well, that's the same thing with like how we do things with directories. We just prefix it with that hash. Imagine if every single file that you used was prefixed with that hash, that layer hash that you might otherwise be familiar with from the OCI world, but it was just part of like the directory structure. What's nice about that is now it's not going to conflict. Now they're conflict-free because you're never going to rewrite them. You're never going to mutate them. So now it could be write-only. And this is how OCI layers work, right? So once you have a layer that has a particular content hash, well, you're not going to mutate it after that. That would change the hash. You still need to like take these things, and right now, the way we normally use OCI layers is you have to kind of do them in order because the contents can conflict. Right? If you have two things in user bin called the same thing, and but they're different contents, now as you combine these things, you end up with a conflict, right? You have to kind of pick an order. You have to pick one to win. How do I distinguish between these things? But if inside of these layers you were guaranteed that there was no conflict, then you have the possibility of doing all this stuff in parallel. I don't even have to check for conflicts because I know by construction there won't be. What's nice about this, for example, in the implementation of this, normally like layers, we use an overlay FS style, or we just kind of copy things on top of each other to generate what we end up using. If everything is conflict-free, I could just bind mount everything much, much faster. I don't have limitations. The 128-layer limitation that we have for layers kind of goes away. I can also reuse them a little bit better, right? Because now other people, it's not going to conflict with, maybe I know it's not going to conflict with me, but other people now also have that guarantee. And so you get much better reuse. And we have a bit more confidence they're not going to interact weirdly. I'm not going to overwrite something. I'm not going to end up deleting something and so forth. So this concept of a conflict-free layer as part of like the standard has promise. So where are we today? Right now, this is just meant to be like kind of like a reference slide. We can't go over everything right now. There's been a bunch of work of people exploring stuff. So kind of this history of this, a little while ago, there was like this blog post about, hey, how do we optimize Docker layers? And the idea was, hey, let's grab all these directories that are conflict-free, and let's kind of run them through a little bit of a like popularity, like topological sort contest, and that's one way to layer our containers. Let's grab all of them, as many as we can, until we run to the layer limit, and then at the very end, we'll just kind of put everything else into one like last final layer. We have people kind of working on things like, hey, how do we deliver containers kind of in a very dynamic way? The Nixery people did this. We started working on things like, how do we stream these builds, right? There's no reason to materialize them all at once into like your like local system. If I have all these directories, and again, they're conflict-free, I could do this in a streaming fashion. There's a PDT Partners did some work with this thing called Nix Snapshotter. This is so that you could run you could run your Kubernetes in a way where the layers are actually grabbed and bind mounted in, right? That bind mount trick we talked about earlier is now used rather than overlaying all these layers. That gives you efficiency gains, it gives the ability in terms of like less storage, faster startup times. We wrote about like how this can kind of, how these containers and NICs are antithetical technologies, but actually can work together. There's some work right now in NICs packages where you can kind of apply custom strategies. So more complicated layering strategies can be applied, not just a matter of saying which one's more popular. Let's say for a fact a certain package or a certain kind of piece of content is going to be reused often. You could kind of extract that from the rest of the graph. Additional work. Replit did some work in terms of having how do we combine these things? How do we kind of get benefits of caching? Because they're trying to have large images, and a lot of their large images have a lot of similarities, and they started losing caching with their existing Dockerfile approach. And so by using this concept called overlay stores, they were able to get a lot of benefits, a lot of speed ups. So a lot of stuff to go read, a lot of references to go into, but people are exploring and designing kind of things along these lines. So here's a game plan. Let's make each directory a layer. Okay, that's one way to easily integrate with the existing technology, the existing frameworks. Sometimes run into problems here because, well, we run out of layers. Let's say you have something that's complicated, that's a large composition, some big ML framework, some AI stack. You might not be able to just say, hey, each package is its own layer, because you might have too many. Okay, well, what if I kind of combine packages, kind of create hey, here's a standard group, a standard chunk. I could start to fit within the layer limitations. Okay, that's nice. It's not as appealing as I would want it to be, but it's a tactic. I talked earlier about this custom strategies, right? We can say, hey, apply different strategies. I don't even know what strategies we might come up with, but that might be something we might want to do. All right. What else can we do? What if we just teach OCI about this concept? What if we just tell them? What if we just show OCI the manifest format, the runtimes that we have, that this thing I want to exist in my container can't conflict with any other similarly defined things in terms of the store paths and all that. And then now that limitation of how many layers I can use basically can just go away, right? It can be implemented kind of inside the engine in a more efficient manner. So that's kind of upstream work that's making this kind of more of a standard. Oh, yeah, so the question was, why is there a limit on the number of layers? So the way kind of this was originally, there's different implementations, but the original implementations of how layers are implemented in the container runtimes use overlay FS. So they kind of give you one layer of a root directory, kind of tarball. They splat it out into disk and then go, cool, now you have another layer, but when you splat out the next layer, you have to check, well, am I overwriting something that already existed? Am I deleting something that existed, but with a little tombstone marker saying, get rid of it? Do I need to modify them? And so you have multiple of these overlay FS mounts on top of each other, and you can sometimes do this dynamically, or you can kind of materialize it as you go, but this becomes a slow process because it's very serial. You have to do it one by one by one.
Just again, going back to the mental model, right? Each one of these actually produces a file system. The file systems have to be overlaid on top of each other. So when containerd or CRI-O, your container runtime, or Docker, actually wants to go and get the OCI artifact that comes out of this, each file system actually has to be copied into a new overlay. And so even starting a container has a big kind of performance hit as you construct the container file system. But then even at runtime, this isn't free. So when you are reading a file or statting a file, any of the file system calls, in an overlay, you need to potentially traverse from the last layer all the way to the beginning to find what you're looking for. And so the mount system call for overlay has a limit to the number of these middle directories that you can mount. And it's because of that limit in the Linux kernel's implementation of overlayFS that then there is a canonical limit in all of the container tooling. And this is kind of just permeated and it is a trade-off. And what that means is that if we have software that depends on more than 120 things effectively, then we cannot represent all of those things as a layer. Unfortunately, any sort of trivial program that you might build could easily start to be 5,000 or 6,000 dependencies, or maybe even 20 or 100,000 dependencies. There's a question over there. The number being the layer limit. So that layer limit, again, comes from a limit to the amount of arguments that you can pass to the mount call on an overlay file system. Yeah, it is a little bit arbitrary, but it does have a performance cost.
Yeah. So,
and so we're going to get to how we can teach OCI about doing things in a non-conflicting way. The spoiler alert here is that what if we didn't use overlay? What if we used a bind mount instead? Containers we can already create with bind mounts, but you cannot construct an OCI manifest right now that tells something like container.D or cryo to do a bunch of bind mounts from some content addressable store. And so that's why we would need to teach OCI. Sweet.
Yeah.
I mean, it's a good diatribe on that.
You're right, though. Like, there is no reason that you can't kind of extend that limit, but if the system doesn't understand that these are non-conflicting, then it's going to have to check every single one on that list, and that's a very kind of yeah, actually, it slows down. Like that's a big piece of the startup time for containers. I don't have numbers at the top of my head, but I mean, that limitation is there because in practice it was found to actually be a limitation. So they said once you get past a certain number, it starts to kind of not be practical anymore.
I'm not a Linux kernel developer, so I've only ever built kernels, not modified them. I imagine it's a non-trivial change to how overlay is implemented. But perhaps if you know how, we could get together and try. But it's actually part of the mount command.
All right. So next step on the game plan here. All right, we're going to need some tooling. We'll want to make tooling to make it so that packages are going to live in these immutable reference or in content address paths, right? Right, I told you earlier about hey, you could use Nix as that tooling to make that kind of easy. That's kind of the core way that Nix operates. But this is similar to there's other kind of systems out there that kind of do this sort of work to put things into their own locations and kind of distribute this. So this is not just Nix specific in terms of an idea, but this could be generalized. All right, what do we do after that? I don't know. Maybe other people have ideas. Maybe there's things that would be helpful here. And then after that, we profit. I'm really interested in steps 6 and 7. So if you have ideas on how to make that possible, let me know. OK, so we talked about this a lot in theory. Here's a little bit of kind of comparisons. If you kind of do this in this kind of fashion of putting everything into their own layer, you get some other interesting benefits. One of them is I can get rid of layers that I know I don't need, right? I can just start removing them because I have all these references to them. I know what they are. And I can start trimming things down. So this was an example that kind of someone showed us of, they built their Python application, but then we're done building it, right? They got rid of all their development dependencies, and what was left? The thing was, the number of packages you had were smaller. That's because we got rid of a bunch of things that only were needed during a build time or packaging time. And things roughly similar in terms of other metrics. But the big one that seemed to be of interest, and especially in some communities, the biggest interest is like your number of vulnerabilities goes down because you get rid of so much other stuff that might be there. And I mean, is that a huge difference? In some sense, yes, because vulnerabilities represent paperwork. It represents how many exceptions I need. It represents how many emails I get. It represents how many alerts I get or how much time I spend dealing with it. Even if I know for a fact that all 62 of the remaining ones are false alarms, might have to go convince some auditor that that is. And might be more expensive than anything else I might do. And that might dominate. So one aspect of something we found along these lines is just let's reduce the amount of paperwork we do. It's not just technical optimization, but bureaucratic optimization. Something that I've talked about sometimes is you have like this difference between like the build time and runtime graph. Obviously, this is like the reason we have multi-stage builds. This is just kind of an example of like, hey, you almost always need a lot more to build something than just to run something. Obviously, there's some pathological examples where that's not the case, but generally, it's far less. Yep. Something to call out. We're going to have some similar topic about like optimizing image sizes later this afternoon. It's going to be by Brian Honoff, and go to his talk as well, because it's going to talk about this similar idea of how do I optimize images.
Is that 5 to 6?
5 to 6. Yep. Okay, so a little bit more about the layering strategies concept we talked about. There's a pull request in there that has some of the details of this is being worked on. But just to give people the idea of like managing a graph and slicing it and cutting it is kind of, how do you describe this? It's a little bit difficult to do, but this is something we're starting to work on is, hey, what if I want to like slice out of my dependency graph, in this case, Python? Well, you have to somehow explain, hey, like grab that and all the things it needs, slice it out. And then here what we're kind of showing is for the rest of the graph, just run our like other standard like popularity contest kind of strategy. Then you can imagine like doing more complex things, right? You can pull out, hey, I want to pull out the standard platform for development that my company uses. That's going to be reused. It's not going to, it might have I might have some baseline that doesn't change often. Or maybe I do have a baseline that changes often. And so these different life cycles, I want to pull them out and kind of manage them independently. So this gives you a little more ability to like customize how layers are put together. Question? Yes, so right now this is like working within it, but you can also imagine this being applied when there is no limit. You still might want to do things like, let's say for transport purposes, you want these layers to be of similar size, so you can just process them and transport them all in parallel. Right? Or maybe you just want this for grouping purposes. I want to group some of these together. So it might be reasons either way. Again, maybe we're in that kind of question mark part of the game plan, right?
I think like one interesting thing could be for like signing, if you wanted to combine layers and maybe you're like, oh, I want this particular blob of things that are certified to work together. And like maybe you want it all as one blob. But you could also just sign a manifest.
Yeah.
I mean, in the future, like assuming that parallel transport of a bunch of maybe also compression. Compression could also be another major reason, because as soon as you're separating a bunch of potentially similar things into large numbers of different blobs, then they have to be compressed separately, so unless you then, I guess, wrap them all up again and then maybe try to compress them again. So that could be another reason, is trying to balance compression versus separating each individual immutable thing for cache coherency. There was one more question.
Yeah, I'd like to go a bit back and challenge the whole thing. Like, when I build the images, honestly, I don't care about layers. And I want to have my distribution, right? I want to have my production image. I want to have my build image. Maybe a base image.
So I'm going to cut your question early because we're going to run out of time. The principle here, and I'm trying not to cut you off. I really appreciate what you're saying. It's very powerful. I'm going to try to make this point simple. The reason that Nix is really powerful with its binary cache is because each time you use one of those layers, if you're building complex graphs like this, then each dependency is immutable and it's cacheable. And even though you can reproduce it from source, you can rely on the work of a really big open source build server called Hydra. And if we were to cache each one of these layers, say you're building software on your Mac that requires 50,000 dependencies, or maybe let's just say 5, more realistic, and then you make an iterative change, right now, when you build an overlay file system, your CPU must copy and compress each one of those bits of each of the 5,000 dependencies every single time that you build a new artifact, no matter how big or how small your change is. And then every one of those bits then gets pushed to a registry, probably from a CI system, and then it gets fanned out. So we are creating a lot of entropy and a lot of copies of the same exact bits over and over again. But if we can get to a place where the layers themselves are the individual derivations, you can pull down 5,000 things, change 10 things, only push 10 things instead of recompressing 5,000 things. And then when it fans out to potentially an entire open source ecosystem of millions of users, like say the Kubernetes base image, then all of those dependencies can be cache hit from stuff that's already there. And then each one of those derivation, or those OCI, content addressable blobs does not need to be scanned again because of the immutable reference. And we're going to run out of time for a demo, so let's try to table the question to the end.
We'll that for 10.
Yeah.
You know, happen?
Huh?
Happen?
Yeah, are you going to skip the Docker tools?
Yeah, we'll do yours, yeah.
Let's go right to the Kubernetes stuff. Let's do this thing. So I don't need the HDMI, I just plug in the USB-C, right?
I think it needs the HDMI.
I have to use the HDMI? Where's the dongle? Here it is. All right, friends, I have something cool to show you. The first bit is a variation of something you've maybe seen before in other Nixie Kubernetes types talks. So, hey, maybe this whole layer thing might work out, right? So we had Tom talk about the Docker tools inside of the Nix libraries that you can use to build your own custom layer strategies. Works great if you're trying to stay within the layer limit. Tom and I were working on a proof of concept with folks who had a very large build cluster. And in that build cluster, what they wanted to do was have the power of Nix every time somebody created a build. And the build would run in a Kubernetes pod, and it would have access to some storage that you could get from somewhere, right? And so we built this initial demo with a read-only Nix store. Again, that Nix store, if you've never seen one, it looks, oh, hey, my pushes are all done. What a Nix store sort of looks like. If let's just close this here. So list the Nix store that I have on this GitHub code spaces. By the way, this code spaces is going to be in a repo after this if you'd like to reproduce our demos. So each one of these is a hash of some piece of software that is immutable that we got from the public build system. And like if I go and I can look at what's inside of, say, JQ, inside of Nix store. Right, so I've got a bunch of different JQ related things. Some of them are from different versions, and you can see that we sort of have this file system hierarchy type looking thing. Hopefully the text is large enough for folks to see, right? So inside of Nix store, we have some folder that doesn't conflict with the other things, and now we have a bunch of rootfs style things. You can see this data structure actually looks somewhat similar to a Docker file. the resulting OCI artifact. What if we found some way to get these folders into a pod a different way? And so the idea when we were working on this proof of concept was, let's first start with a read-only store. And I'm just going to show the Kubernetes manifest, and again, we're going to push this into a repo. I have it running in a cluster as well. We'll see how much we can look at. This is the read-only store example. And we wanted to be able to mount that store from somewhere underneath. And then when we create our build pod, that we would be able to then pull other things from a Nix cache into the pod. And so this is a deployment with a build runner. The build runner creates a privileged mount manager because we need to mess with mounts. Technically, you could provide some more granular capabilities here, but this was just a proof of concept. This image here, we basically made a small base image with Nix in a different route so that it wouldn't collide with the things that we would be mounting a new Nix store from. And then we have a little shell script inside of the mount manager container here. And what it does is it makes an upper and a work directory for an overlay file system, and then mounts an overlay with a lower directory and an upper directory and a work dir. By the way, this is where that layer limit comes from, and it's what you would need to modify. Also, we're using overlayFS here, but I've heard that ButterFS does overlays maybe potentially in a more performant way, so that's also something as an aside that you could look at, is ButterFS. And then we would be able to touch something in that store and just make sure that we could add files. And we have some volume mounts in the mount manager where we are getting volumes from the host system. So what this means is that we need to land a Nix store on each of the little hypervisors or the little worker nodes inside of a Kubernetes cluster. So we grab the host data / Nix, call that the host shared Nix, and then we create an empty directory for the Nix in container mount, and then we also make an empty directory for an overlay file system. So the mount manager populates that overlay file system directory, and then it creates the Nix in container mount. And that mount propagates bidirectionally. And then for lifecycle, when this container stops, we have to unmount it so that we don't end up with zombie mounts on the system. Super hacky. Now we can create our user build container, which is unprivileged and not running with root. And then we hop in there, and we should be able to do Nix stuff as long as the volume mount has a read-only access to the Nix in container mount that the mount manager container just created. Now, how do we get the stuff from the host to be useful? Here we have a Nix host manager. We mount the stuff from the host. We are not using read-only access. We have write access to it now. So even so, like the container with the mount manager was doing everything read-only. But then here in the host manager, as a daemon set across all of our cluster nodes, we can then declare that we would like certain Nix packages to be there. And because we are using Nix, all of the dependencies of those packages will then populate inside of our Nix store across the Kubernetes cluster. I don't want to run out of time here to show you something super cool, so I'm going to leave it at this as far as the shared Nix demo. But you'll see that we have a different version here with overlay that has an overlay file system underneath at the host level, where we could also do read-write changes to the host store and then read-write changes in the containers at the same time. And this works. It's cool. You've seen similar demos before, potentially, if you've gone to other Nix-type, Kubernetes-type talks. Now I want to show you something also Kubernetes-specific. Oh, and this runs in kind. You can see that if I get the namespaces on this Kubernetes and Docker cluster, we have a bunch of these proof of concept namespaces. Again, this will be in the repo if you want to reproduce. The next thing I want to show you relies on the cryo container runtime currently. It uses a feature that's currently in beta in Kubernetes 132. It's called image volumes. So with image volume, what we can do is we can actually create a volume that comes from a container registry. So we get the entire rootfs of some other container's overlay file system, and then we get to use Kubernetes to tell the runtime to pull that into storage if it's not present on the machine already, say for this pull policy, or you could say always. And then we can use volume mounts to mount that into some container of some pod and decide where that goes using a bind mount. Pretty cool. I thought, gosh, wouldn't it be nice if we built a demo for that using Nix? And that's what I've been doing this morning. I have this shell script that will create a deployment based off of, I think the base image here is Alpine Linux. We're just going to sleep forever. And then we've got a list of volume mounts. In the list of volume mounts, there's just some demo stuff. But then I'm also going to mount a database from a working Nix installation. And then we're going to loop over the store paths from Nix store. I have this limited to 260 paths, which I already know will work. But technically, I think I have 384 paths that I'm moving from this GitHub code space into a Docker registry as a bunch of individual container images. And then for each one of those store paths, I'm going to iterate a counter, create a volume for that counter, or this is technically a mount. I'm going to mount that volume at Nix store/store path. And then we are going to create the volumes list for the pod, and we have to have a matching volume. So again, for every store path in Nix store paths, let's make sure to keep the same counter in the same order on the same collection. And then we will grab an image volume with a reference to, on my Docker Hub account, StealthyBox, a repository called Nix store, where each tag of that container image is the rootfs looking thing from inside of Nix store on my GitHub code spaces. And then I have a little script, one for pushing var nixdb. So basically you copy star from nixdb, which is a build context, into the Docker image and just push it. And then same thing for a Nix store path. So you can say push path, some store path, and then it'll go and get that store path from the Nix store build context, push that up to your Docker registry. So you'll see if I pop over to StealthyBox Nix store on Docker Hub, then inside of my container image tags, I could say, look for kind. And now I have the binaries for Kubernetes in Docker at version 2.6 and version 0.27 with its hash as if it came from a Nix store, and this came from my GitHub code spaces when I ran that script. Similarly, I think I have a NixDB repo, and I just named this NixDB code space scale. So if I wanted to actually use Nix inside of the container and have a valid database for every path that I pushed, then that's like one way to do that. That means that if we run our script, which looks like this, gen deploy, and then we produce a YAML file, and then our script produces a Kubernetes deployment with a bunch of volume mounts to a bunch of Nix stores that there's 260 of them in here, so it's twice as much as the layer limit and more. And then for each one of those volume mounts, we have a matching reference to Docker.io, StealthyBox, Nix store, and then some Nix store path if it's not present already on the machine. So basically, if I do a kubectl apply, and then the file, and I do a deploy image volumes YAML, you'll see that I have an unchanged manifest here, which means that if I get the pods that are currently here. We have container creating. So what this means actually is if I describe that pod, I just sort of have a lot of store paths. It's like 2.8 gigabytes of, oh yeah, so I've reached my unauthenticated pull limit for Docker Hub because that's 260 different images. But then a bunch of these other ones are already present on the machine. Luckily, I did this earlier, but with 40 store paths. So if I show this one, which is already running, then I should be able to exec into it. So this running one, kexec, interactive. I'm going to start a shell session, and you'll see that if I go to /nix var/nix db, I have the same database that came from my GitHub code spaces. And then similarly, if I go into Nix store and I do a little list, I've got a bunch of Nix store paths populated inside of my container. Each one of these Nix store paths comes from an independent overlay file system that was constructed for an independent container image that is all stored under the same repo. I've got, if I just like filter for one, which like most hashes should probably have a 1 in them, you can see that I've got 25 results per page, and there are currently roughly 13 pages. So that's 300 or so store paths on my Docker Hub account that I just pushed while Tom was speaking. And now I can actually go and run software. Maybe, do I have a bunch of libraries in here? There's only 40. Here's kubectl. Let's go into here, and there should be a binary directory, and I should be able to, oh, it's kubectl convert. I don't know what that is. Not sure what that is, but it's a binary and it runs and it works, and it's from the Nix store on my GitHub code space. It's that same exact store path. So there is one experimental way to get hundreds of different things beyond the layer limit into Kubernetes. And I would say that the only limits you're going to run into here is that usually with Kubernetes we don't like to store manifests that are greater than 2 megabytes. So if we look at how big the manifest actually is with 260 things, then it is 73 kilobytes. And yeah, that's constructing an image by abusing image volumes inside of Kubernetes, running them so that you can use your Nix software, and you don't have to have anything new. We don't have to change any standards in order for that to operate. My only criticism of this is it wouldn't scale to anything past 2 megabytes, so if you wanted to do like hundreds of thousands of things in a Nix store, then it probably would stop working because etcd just doesn't like that. And obviously this is not what this is for. I think this was produced, this feature became a beta feature that you can enable on a Kubernetes cluster because some people wanted to mount some like AI models, and I'm using it for this instead. But I think it's pretty performant. Mainly you need to be able to pull a lot of images onto a machine. If you're running your own Docker registry, that's not a problem. Or if you're pulling from GitHub instead of Docker Hub, that would be perfectly fine. And then also I'm unauthenticated. So if I authenticated with Docker Hub, I wouldn't have the rate limit. And my last criticism of doing this is we shouldn't need Kubernetes to be able to tell a container runtime to bind mount a bunch of content. And so that gets into sort of the last point, which is we can do a node local Nix store by sharing var Nix, or /Nix from the host. We can do image volumes where we can push Nix databases and Nix store paths independently as container images that you can then reference, and you can abuse Kubernetes or a similar orchestrator to do a bunch of bind mounts. This demo would be really cool, and you should go to Brian's talk at 5 o'clock. Nix Snapshotter extends container.D, which is one of the options for container runtime, so that you can get store paths directly from a Nix daemon. And the way that it extends container.D is by adding annotations to the OCI manifest to tell this special piece of software where to find the paths. And you can mix these Nix store paths directly from a Nix daemon with regular overlay layers from standard OCI images. This would be a cool thing in the future, especially for development, where you have a Nix daemon and container.D running on the same machine. But a glimpse of the future would also be then a similar piece of logic that is standard in container.D that does not need any Nix protocol so that you could actually ship your artifacts, and it would also work for like RPM OS tree and those kinds of things. But yeah, that's pretty much most of our homework on figuring out how we can make cloud native Nix a thing. And we are over time a little bit, so we should probably close this out. Call to action is let's bring reproducibility, flexibility, and efficiency to containerized workflows. Kubernetes gives us an orchestration layer. It also gives us this weird alpha or beta feature that we can use to maybe even construct images in a Nixy way. How could we put those things together to do real cloud native Nix? Be really cool. If we have time for questions, Tom and I would love to talk to all of you about it, and of course, also freedom to the Scale organizers to kick us off stage. What do you think, Gwen?